A few days ago, Klein posted this on their X account. They gave Opus 4.8 and GLM 5.2 the same task, a bug from their own codebase. Both were able to solve it. GLM used twice as many tokens and took 3 times longer and was still cheaper than Opus. And on the code quality side, GLM cleaned up that code and verified the build compiled before finishing. Opus skipped that. It left type errors that passed the test but broke the production build, so that's what we're looking at today. GLM 5.2. What is it, how it works, and why it performed the way it did. GLM 5.2 is designed to work autonomously through complex code bases across thousands of sequential steps over hours without losing track of the objective. And to do that, the model needs to hold a huge amount of context at once, about 1 million tokens. Now you might be wondering, why is that actually hard to build? Seems like you'd just give it more memory and move on. But the problem isn't storage, it's attention. So what is attention doing here exactly? Every time the model processes a token, attention is figuring out which previous tokens in the sequence are actually relevant to it. And the cost of doing that doesn't grow linearly with context length. It grows quadratically, meaning the longer your context, the more that cost explodes. At 1 million tokens, that becomes completely unworkable. So what if instead of attending to every single token, we had something that first scanned the context and only surfaced the relevant ones? That's the basic idea behind what GLM uses called DeepSeek sparse attention. A lightweight indexer that scores the prefix and selects only the top k relevant positions per query. Instead of every token checking every other token, it's now only checking a small handpicked subset. The compute cost drops dramatically, but now the indexer itself becomes a problem. It still has to score the entire prefix on every query at every single transformer layer. At 200k tokens, it was eating up 81% of prefill time just doing that. So let's look at what the indexer was actually selecting across layers. Turns out adjacent layers were independently choosing almost identical tokens, between 70 and 100% overlap. The model was recomputing the same result over and over again. So what if you just ran the indexer once every 4 layers and let the next 3 reuse it? That's index share. That one change cuts per token compute by 2.9x at 1 million token context and eliminates 75% of indexer work entirely. And that's what makes the context window viable at this scale. So how does it perform in real-world tests and benchmarks? On SWBench Pro, which measures whether a model can resolve tough GitHub issues autonomously, GLM scored 62.1%. That puts it above GPT 5.5 at 58.6% and makes it the strongest open-weight model on that benchmark. On Terminal Bench, which tests real-world terminal task completion, GLM scored 81. Opus 4.8 sits at 85. On the Artificial Analysis Intelligence Index, GLM scores 51. Claude Fable 5 is at 60. GPT 5.5 is at 55. GLM is right below both of them, and everything else that's open weight is behind it. So it's not betting the frontier, but it's the closest any open weight model has gotten. Now here's where it gets interesting, because performance alone doesn't tell you much without looking at what it actually costs to run. Opus 4.8 is priced at $5 input and $25 output per million tokens. GLM is $1.40 input and $4.40 output, and because it's open weight, third-party providers have pushed that even lower, down to around 72 cents per million tokens with quantization. On the AA Briefcase benchmark, which simulates multi-week knowledge work across thousands of corporate documents, the average cost per task came out to $2.40 for GLM, Opus was $10.40, Fable 5 was $31. So you're getting performance that's close to Opus at roughly a quarter of the cost. GLM is token heavy. On the Artificial Analysis benchmark, it consumes around 43,000 output tokens per task on average. Of those, about 33,000 are just internal reasoning traces before it even produces an answer. That's significantly more than its open weight peers. And in max mode, it has a tendency to overthink. Instead of acting, it goes into exploring every edge case, generating walls of reasoning, sometimes loops through its own correction without ever landing on an answer. Kinda like a death spiral. From personal experience, asking to build a full-stack end-to-end app consumed roughly 3 million tokens. There were minor errors, but noticeably fewer than other open-weight models on the same task. So the token inefficiency is there, but so is the output quality. And when you look at where the other open-weight models actually sit on the benchmark, GLM is in a different tier, which makes it hard to reconcile what you're paying with what you're getting. The other limitation worth knowing is that GLM is text only. There's no native vision, so anything that involves reading a UI mockup or diagnosing a visual layout, you'd need to pipe in a separate vision model to handle that first.